Welcome to QHSE Talks, where we break down the science, systems, and stories shaping our planet's future. Let me start with a quick picture. Imagine standing outside on a warm day. The sunlight hits your skin, the air feels still. But what if I told you that invisible forces are quietly wrapping our planet in a thicker and thicker layer of heat? That's not science fiction. That's our reality. Every breath we take, every light switch we flip, every product we use connects to something happening high above us, in the thin shell of gases that make life on Earth possible. But here's the twist. That same atmosphere that protects us is also trapping more heat than ever before. And it's not because the sun got stronger or space changed its mind. It's because of us. Our cars, our industries, our daily habits have tipped a delicate balance that took millions of years to form. And the culprits? They're not villains in a movie. They're invisible, odorless, and floating all around us. Carbon dioxide, methane, nitrous oxide, the so-called greenhouse gases. They sound harmless, maybe even technical, but together, they're rewriting Earth's climate story, one molecule at a time. In this episode, we're unpacking how these gases actually work, how they trap heat, how we measure their impact, and what makes some far more dangerous than others. Because understanding them isn't just about science. It's about seeing the blueprint of our own future.
So let's jump right in. Let's start with the absolute core definition. What are we talking about?
Okay, global warming. Our sources define it very clearly. It's presented not as some, far-off theory, but as a direct result of human activity.
Human activity. That's key.
Yes. And it's characterized by this recent and ongoing increase in the global average temperature, specifically near the Earth's surface.
And this isn't just a number on a thermometer, is it? This temperature rise, it has real, tangible consequences.
Oh, absolutely. The sources are packed with details on this. You see rise in temperatures, obviously, in the oceans and across the land surface.
Which then causes other things.
Precisely. These drive critical secondary effects. You've got the obvious one, rising sea levels. Then there's the accelerating melt of polar ice cover.
Glaciers, Arctic sea ice.
All of it. And also really disruptive changes to water cycles. So more intense floods in some areas, deepening desertification in others, and even strange seasonal things like excessive snowmelt at unusual times.
So they're all connected, these symptoms.
They're all interconnected symptoms, yes, driven by that core increase in the planet's energy budget.
And the driver for that energy increase.
Oh.
That brings us to the main subject, greenhouse gases, GHGs.
Right. The definition itself is pretty simple. A GHG is basically any gas in the atmosphere that can absorb infrared radiation.
Heat, essentially. They trap heat.
Well, trap heat, making the atmosphere act like a heat trap. Our material lists the big ones we need to know about. There's carbon dioxide, CO2, methane, CH4, nitrous oxide, N2O, ozone, O3.
Okay, those are the common ones?
And then this huge family of synthetic industrial gases. These are really important when you get into policy and specific impacts.
Right, the manufactured ones?
Yeah. Things like chlorofluorocarbons, CFCs, hydrochlorofluorocarbons, HCFCs, hydrofluorocarbons, HFCs, perfluorocarbons, PFCs, and the big one, sulfur hexafluoride, SF6.
We hear a lot about CO2 and methane, maybe because there's so much of them.
And rightly so, by volume they dominate. But the potency, the sheer warming power per molecule of some of those industrial gases, well, that's where the real shock lies. We'll definitely get into those staggering numbers later on.
Okay, let's start with the basic science then. The essential mechanism. How does this work? It all starts with the sun, right?
It does. The sun emits energy across the electromagnetic spectrum. Most of it arrives here as visible light.
Which hits the Earth.
Right. When that energy hits the Earth's surface or atmosphere, some gets absorbed, warming things up, and some gets reflected or re-radiated back towards space.
But not all of it escapes.
Exactly. The energy that's re-radiated from the warmed Earth isn't visible light anymore. It's longer wavelength infrared radiation. Basically heat.
Okay. And this is where the GHGs come in.
This is precisely where they come in. The molecules of these greenhouse gases, the water vapor, the CO2, the methane we mentioned, their physical structure is just, well, perfect for absorbing specific frequencies of that outgoing infrared radiation.
So they catch the escaping heat.
They intercept it, yeah. The molecules absorb the energy, they vibrate, get energized, and then they re-radiate that heat, Critically, they radiate in all directions, including back down towards the Earth's surface.
Like a blanket.
It's the perfect analogy. They act like an insulating blanket around the planet. Or, the classic greenhouse effect.
So more GHGs.
Means a thicker blanket, which means more trapped heat, less escaping to space, and ultimately higher average surface temperatures. That's the fundamental process.
Now, here's where the sources threw up something really interesting for me, the history. When did we figure this out? You tend to think of climate science as, I don't know, a recent thing, maybe the 70s or 80s.
Yeah, that's the common perception. But the material points us way, way back to a figure many people haven't heard of, Svante Arrhenius.
Arrhenius, Swedish chemist.
And get this, back in 1896.
1896?
1896. He was the first person to scientifically quantify this whole idea. Think about that context. This was long before the Industrial Revolution had really hit its global stride.
So what did he actually claim?
He had this, startling foresight. He claimed that burning fossil fuels coal, primarily back then, would increase CO2 levels in the atmosphere, and that this increase might eventually lead to enhanced global warming.
That's incredible for the late 19th century. Was he just guessing?
Not at all. That's the amazing part. He wasn't just speculating vaguely. He actually proposed a specific, calculable relationship between the concentration of CO2 in the atmosphere and the resulting temperature change.
He did the math. He even calculated
the effect of the natural greenhouse effect, the warming we get just from existing CO2 and water vapor.
So the effect that makes Earth habitable in the first place.
Precisely. His calculations showed that thanks to the natural infrared absorption by water vapor and CO2, the Earth's average surface temperature sits around a comfortable 15 degrees Celsius.
Without which?
Without that natural blanket, the planet would be a frozen wasteland, probably around -18 Celsius on average, uninhabitable.
So his work established the baseline, the fact that these gases fundamentally control our climate.
Okay, but here's the bit that really jumped out from the sources, this massive historical footnote. You said he quantified it in 1896.
Yes.
But that foundational idea, the precise calculation of how much warming you get from CO2, it wasn't actually verified until 1987. Isn't that astounding, that 91-year lag? It just highlights how incredibly complex atmospheric science really is.
Why did it take so long?
Well, Arrhenius had the basic chemistry and physics right, but think about what was missing for decades. Scientists lacked the tools. They didn't have high-altitude balloons or satellites for atmospheric monitoring. They didn't have the sophisticated sensors needed to measure the specific absorption bands of infrared radiation way up there.
And computers, presumably.
Crucially, yes. They lacked the sheer computational power needed to model the incredibly complex three-dimensional flow of energy through the atmosphere, considering oceans, clouds, everything. The 1987 verification wasn't just confirming his idea. It was a triumph of technology finally catching up to his, 19th century theoretical genius.
So the science kept ticking along, building on his foundation.
It did. Through the mid-20th century, the picture got clearer. In the 1940s, for instance, researchers provided empirical proof in the lab. They showed directly that if you increase the amount of CO2 in a sample of air, it demonstrably absorbs more infrared radiation.
So the direct link was nailed down experimentally.
Correct. The lab work backed up the theory.
And then there's a finding in the 1950s about how long CO2 stays in the atmosphere. Our sources mentioned this caused some confusion.
Yes. This is a really important point to clarify because it's been misused or misunderstood over the years. Early research in the 50s suggested that CO2 had an atmospheric lifetime of about 10 years.
Okay, 10 years. That sounds short, like the problem fixes itself quickly.
Exactly. If you hear that figure today without context, you might think, oh, okay, stop emitting and it's gone in a decade. But that is not what it meant.
So what did it mean? Let's really clarify this.
That 10-year figure referred to the average residence time of an individual CO2 molecule in the atmosphere before it gets, say, absorbed by the ocean or taken up by a plant through photosynthesis. It's about the speed of the natural carbon cycle, how quickly molecules are exchanged between the atmosphere, oceans, and land.
But that's not the same as the lifetime of the extra CO2 we're adding.
Precisely. That's the critical distinction. When we burn fossil fuels, we're adding a huge pulse of excess CO2 into the system, far more than the natural cycle is built to handle quickly. The natural sinks, oceans, forests get overwhelmed.
They can't keep up.
So while individual molecules might cycle through in roughly 10 years on average, a significant fraction of that excess CO2, the extra blanket thickness causing the warming, actually persists in the atmosphere for a very, very long time. centuries, even millennia for some of it.
Okay, so the 1950s data was about the molecule turnover rate, not about how long the warming impact of our emissions lasts.
Exactly. It described the speed of the cycle, but it totally missed the long-term accumulation problem caused by human emissions piling up faster than nature can remove them. That's a crucial nuance.
Before we move to the hard data on current changes, we absolutely have to talk about water vapor. The sources flag this.
Yes, the elephant in the room in some ways. Water vapor is by far the single most abundant greenhouse gas in the atmosphere.
Much more than CO2.
Oh, vastly more, in terms of sheer volume and its contribution to the natural greenhouse effect. Which is sometimes why it gets sidelined in discussions about human-caused warming, because we don't directly emit water vapor on a climate-altering scale like we do CO2.
But it plays a role.
A huge role. But it's a different kind of role. Water vapor doesn't initiate the warming trend we're seeing now, it amplifies it. It's central to a critical feedback loop.
Okay, a feedback loop, how does that work?
Well, our sources detail this self-reinforcing mechanism. It starts with the initial warming caused by the GHGs we do emit, like CO2. As the atmosphere warms up even slightly,
More water evaporates.
exactly. More water naturally evaporates from the Earth's surface, oceans, lakes, rivers, soil, plants. And critically, warmer air has a higher physical capacity to hold more water vapor. It's just basic physics.
So warmer air holds more water. And water vapor is a greenhouse gas.
Right, so you get this cycle. The initial warming from CO2 leads to more water vapor in the air. More water vapor means more infrared heat gets trapped. More trapped heat means the atmosphere warms up further.
Which leads to even more evaporation and more water vapor.
Precisely. That's the loop. Warmer, more evaporation, more water vapor, warmer on more evaporation. It's a powerful amplifier of the initial warming signal.
Is this the runaway greenhouse effect concept the sources mentions?
It's the core of it, yes. It's a massive accelerator. It takes the initial warming from our emissions and ramps it up significantly. And it also drives changes in global precipitation patterns, where and how much it rains or snows.
That sounds potentially really dangerous.
It's why scientists worry about it so much. If this feedback mechanism gets pushed too far, too fast, it has the potential to turn a serious problem into something much, much worse. It's thought to be part of what happened to Venus, turning it into the inferno it is today.
Okay, so water vapor is the accelerator, amplifying the effect of gases like CO2. What does all this theory, that the mechanism, the history, the feedbacks actually translate to in terms of measurable changes now? What's the hard data?
The sources point to very specific findings, particularly citing NASA data. The global average temperature has definitively increased. The number given is 0.19 degrees Celsius since 1880. 0.19 degrees C. Honestly, that sounds quite small. Less than a fifth of a degree over more than a century. It does sound small, doesn't it? But you have to understand the context of that number. That seemingly tiny fraction of a degree represents an absolutely astronomical amount of extra energy absorbed and stored by the entire planet.
Where does that energy go?
Primarily, the vast majority goes into the world's oceans. They have a huge capacity to absorb heat. Think about heating up a massive bathtub. Even a tiny temperature rise requires a colossal, sustained input of energy. That 0.19 degrees is a signal of a profound energy imbalance in the Earth system.
We can see the effects of that stored energy elsewhere.
Directly. Look at the planet's cryosphere, the frozen parts. The data on Arctic sea ice is particularly stark and cited in our material. The minimum extent reached each summer.
The lowest point of the melt season.
Exactly. That minimum extent has been reducing by an average of 13.4% per decade.
13% per decade, that's huge.
It's incredibly rapid. That's not a model prediction, that's direct satellite observation. It's physical evidence of that store heat doing work, melting ice at an accelerating rate.
And this science isn't standing still, right?
Yeah.
The models, the data.
Not at all. The sources make a point of this. The data is constantly being gathered, checked, cross-verified, and renewed. Climate models are continuously updated and adjusted as new data comes in and as our understanding of the physics improves.
So it's an evolving picture.
Absolutely. It reflects a commitment to rigorous science, constantly testing and refining, not clinging to old ideas. It's about following the evidence.
Okay, so we understand the mechanism. We see the evidence of change. Now let's shift gears a bit and talk about the different impacts of these gases. You mentioned earlier that not all GHGs are created equal in terms of warming.
That's right. We need to move from what these gases are to how effective they are at actually trapping heat, at thickening that planetary blanket. Some are vastly more powerful than others, even if they're present in much smaller quantities.
And there's a specific way to measure this difference.
Yes. This brings us to a really crucial concept, especially for policy and regulation: the global warming potential, or GWP index. The definition sounds a bit technical, but it's essential to unpack it.
Let's try. How do the sources define GWP?
Okay, the formal definition goes something like this. GWP is an index based on the radiative properties of the gas, measuring the radiative forcing following a pulse emission of a unit mass of a given GHG, integrated over a chosen time horizon relative to that of carbon dioxide, CO2.
Wow, okay. Let's break that down. Radiative properties and radiative forcing, that's just about how much heat it traps, right?
Essentially, yes. How effective it is at absorbing that outgoing infrared radiation. Pulse emission of a unit mass just means we're comparing the effect of releasing, say, 1 kilogram of the gas all at once.
Okay. And integrated over a chosen time horizon. That sounds important.
It's critical because different gases last for different amounts of time in the atmosphere. Some break down relatively quickly, others stick around for centuries or millennia. So to compare them fairly, we have to pick a standard time frame over which to measure their impact.
And what's the standard?
Usually the standard time horizon used for policy and reporting is 100 years.
Wait a second. If we choose 100 years, but you just said some gases last for thousands of years,
Yeah.
aren't we kind of undercounting their total impact?
That is an excellent point, and it's a known limitation, or rather a feature of the GWP index. You're absolutely right. The 100-year horizon is fundamentally a policy choice, a compromise.
The compromise between what?
Between capturing a significant portion of the warming effect for most gases and providing a manageable timescale for policy decisions. For those really long-lived gases, especially the synthetic ones, their total warming effect over their entire atmospheric lifetime is indeed much greater than their 100-year GWP suggests.
So the GWP number is more like a snapshot relevant to near-term policy.
Exactly. It's a standardized tool for comparing relative potency over a timescale decision-makers can grapple with, even if it doesn't capture the full multi-century legacy of some emissions. It's important to remember that limitation.
Okay, so within that chosen time horizon, GWP reflects two main things.
Two key factors, yes. First, how long the gas actually persists in the atmosphere during that period. Second, how strongly it absorbs energy, its radiative efficiency during that time.
So higher GWP means?
Higher GWP means more warming per kilogram released compared to CO2 over that 100-year period. It makes a gas a much more potent warming agent, even if its concentration in the atmosphere is tiny, measured in parts per billion or even trillion, compared to CO2's parts per million.
And because of these huge differences, we need a way to add them all up. You can't just compare kilograms directly.
Correct. We need a common currency. And that currency is the carbon dioxide equivalent, usually written as CO2e.
CO2 equivalent.
Yes. It's the standard unit for comparing the warming impact, the radiative forcing of any greenhouse gas, back to the impact of CO2. It lets us talk about a total warming footprint from a mix of different gases.
How do you calculate it?
It's actually very straightforward. You take the mass of the specific GHG that was emitted, say, kilograms or tons, and you multiply it by its global warming potential, GWP value.
Mass times GWP equals CO2e.
Exactly. Mass x GWP equals CO2e. This lets governments, companies, everyone aggregate the impact of releasing maybe a small amount of a very high GWP gas alongside a large amount of CO2 and express it as a single comparable number for inventory and target setting purposes.
Okay, this makes sense. Let's look at the actual numbers, the potency scale using that standard 100-year time horizon. What do the sources show?
Right, this is where the scale difference really hits you. Carbon dioxide, CO2 is our baseline. By definition, its GWP is 1.
Okay, CO2 is 1. What about methane, CH4? We hear a lot about that from, say, agriculture or natural gas leaks.
Methane is significantly more potent than CO2, especially in the short term, because it breaks down faster. Over the 100-year horizon used in older protocols like Kyoto, which we'll discuss, its GWP was typically set at 21.
21 times the warming impact of CO2 per kilogram.
Over a century, yes. Though it's worth noting, more recent scientific assessments often give methane a higher GWP, maybe 25 or 28 or even more, reflecting updated understanding of its impacts, particularly indirect effects on ozone. But let's stick with the source numbers for now. 21 is already substantial.
Okay, 21. Then there's nitrous oxide, N2O, often from fertilizers, industrial processes.
N2O is another step up, potent and long-lived. Its GWP is 310.
310 times CO2. That's a big jump.
It is. But now we get to the synthetic fluorinated gases, the F gases. These are the ones often used in refrigeration, air conditioning, electronics manufacturing, industrial processes. They don't occur naturally.
And they're GWPs.
They go through the roof. Take a common refrigerant replacement, HFC 134A, used in car air conditioners for years. Its GWP is 1,300.
1,300.
Or perfluorocarbons, like CF4, which can be released during aluminum production or semiconductor manufacturing. GWP of 6,500.
6,500 times CO2. These gases are engineered for specific jobs, right? They're stable.
Incredibly stable. That's often why they're useful industrially, but it means they last for a very, very long time in the atmosphere, hundreds or thousands of years, which contributes to those high GWP values.
And then the sources highlight one extreme case, sulfur hexafluoride, SF6.
Yes, SF6. This one deserves special attention. It's an amazing substance in many ways, non-toxic, chemically inert, and incredibly effective electrical insulator.
Where is it used?
Its main use is in high-voltage electrical equipment. Think circuit breakers, switchgear, and power stations and substations. It prevents electrical arcs and ensures the grid runs safely and reliably. Essential stuff.
Okay, but it's GWP.
Its GWP is simply astronomical. Over 100 years, it's 23,900.
23,900.
23,900 times the warming impact of CO2 kilogram for kilogram.
That's almost unbelievable.
It really is. And it lasts for thousands of years in the atmosphere. It means that even tiny leaks from electrical equipment, which are hard to avoid completely, can have a disproportionately massive impact on the climate.
So managing SF6 isn't just about stopping pollution, it's about finding alternatives for a really critical industrial function.
Exactly. It perfectly illustrates the complexity of mitigation. You can't just ban it overnight without finding something else that can safely handle high voltages in our power grid. It underscores the need for technological innovation alongside policy.
So when you add up all these different gases using their CO2 equivalents, what's the total global scale we're talking about?
The numbers are immense. Our sources cite a figure for 2016. Total global greenhouse gas emissions were around 50 billion tons of CO2 equivalent.
50 billion tons.
Annually.
Annually. That's the scale of the blanket thickening we're causing each year. It's a staggering volume that needs to be tracked, accounted for, and ultimately drastically reduced.
And where do these emissions come from geographically? Is it evenly spread? Not at all. The source material is very clear on this. The responsibility is highly concentrated. The top 10 emitting countries globally account for somewhere between 68 and 70% of total annual GHG emissions.
So roughly 10 countries emit almost 3/4 of the total.
That's right, which obviously has huge implications for international climate negotiations. You need action from those key players for the global totals to change significantly.
It explains why progress can feel so slow and difficult sometimes. It requires coordination among those major emitters.
Absolutely. It's a classic global commons problem, but with responsibility heavily weighted towards a relatively small number of actors.
And the tracking gets even more detailed, right? Down to the national level.
Oh, yes. To manage this, you need incredibly detailed inventories. Our sources even mention specific examples like data available for Egypt, their annual share of global emissions, their per capita emissions, a breakdown of emissions by economic sector within the country.
So energy, industry, agriculture, waste.
Exactly. That level of granular sector-by-sector data is essential. It shows policymakers within a country not just how much they're emitting, but where those emissions are coming from. That's crucial for identifying the most effective places to target reduction efforts. Where are the leverage points?
That detailed inventory data you just mentioned, that leads us perfectly in the next part. The specific, quite technical language that's used for tracking and reporting all these greenhouse gases. This is the language of environmental accountants, climate policymakers, compliance officers.
Right. If you want to manage something on a global scale, you need a very precise, agreed-upon vocabulary and methodology. This section is all about that structure.
So where do we start? The foundation must be measurement itself.
Absolutely. It starts with monitoring. The sources define this simply as the continuous or periodic assessment of GHG emissions, GHG removals, or any other GHG-related data.
Continuous or periodic? So ongoing checks.
Yes. You can't manage what you don't measure. Rigorous, consistent monitoring is the absolute bedrock of any credible climate policy or corporate sustainability claim. Without good monitoring, everything else falls apart.
And we can monitor not just the present, but the past, too. How do we know about historical levels? before we had modern instruments.
This relies on one of the most ingenious bits of climate science, analyzing gases trapped in ice.
Ice cores.
Exactly. Scientists drill deep into ancient ice sheets in places like Antarctica and Greenland. These ice sheets have built up over hundreds of thousands of years from accumulated snowfall.
And they trap air bubbles?
Precisely. As the snow compresses into ice, it traps tiny bubbles of the surrounding air from that time. By carefully drilling down, extracting these ice cores, and analyzing the gas composition within those ancient air bubbles, scientists can reconstruct a remarkably detailed history of the atmosphere's makeup.
So we can measure CO2 levels from, say, 100,000 years ago.
Or 800,000 years ago, even further back with some cores. This ice core data gives us that crucial long-term perspective. It shows us the natural range of CO2 concentrations over ice ages and warm periods, validating Arrhenius's baseline idea and highlighting just how dramatically different the current spike is.
And organizations track this historical data.
Yes. Places like the website mentioned in the sources, www.co2levels.org, compile and present this data. The ice cores are like a physical time capsule, providing undeniable context for the emissions we're seeing today.
Okay, so we can monitor present and past. Now let's clarify how gases move through the system. The sources use three key terms: sources, sinks, and reservoirs. How do they relate?
They describe the flow. A GHG source is the most straightforward. It's any process or activity that releases a greenhouse gas into the atmosphere.
Like burning fossil fuels.
Burning fossil fuels in a power plant, driving a car, deforestation, certain agricultural practices, industrial processes, anything that adds GHGs to the air.
Okay. And the opposite?
The opposite is a GHG sink. This is any process that removes a GHG from the atmosphere. This removal process itself is often just called GHG removal.
Like trees growing.
Photosynthesis is the classic example. Forests, plants, soils, oceans, they all act as natural sinks, actively pulling CO2 out of the air.
So source adds, sink removes. What's a reservoir then?
A GHG reservoir is basically a storage component. It's any part of the Earth's system other than the atmosphere itself that accumulates and stores greenhouse gases. Importantly, reservoirs can also release these gases back later.
So sinks take gas out of the atmosphere and reservoirs hold it.
You can think of it that way. The sources give key examples of natural reservoirs. The oceans are a massive one, holding vast amounts of dissolved CO2. Soils store huge amounts of carbon. Forests are both sinks when growing, and reservoirs storing carbon in wood and soil.
Can reservoirs be man-made?
Yes. The sources specifically mention GHG capture and storage, CCS technology, as a process that creates a reservoir. You capture CO2, say from a power plant, and inject it deep underground into geological formations for long-term storage. That geological formation becomes a man-made reservoir.
Okay, source, sink, reservoir. That clarifies the flow. Now, things get more complex when we talk about responsibility, right?
Yeah.
Especially for companies or countries.
Absolutely. This is where corporate reporting standards and national inventories need to be very precise about who is responsible for which emissions. The key distinction here is between direct and indirect emissions.
Direct versus indirect. Let's define those carefully.
Okay. A direct GHG emission, or a direct GHG removal for talking sinks, comes from sources or sinks that are directly owned or controlled by the reporting organization.
Owned or controlled? Give me an example.
Right. If a factory burns natural gas in its own boiler for heat, the CO2 from that boiler is a direct emission for the factory owner. If a beverage company has a CO2 recovery unit on-site capturing CO2 from fermentation to use in fizzy drinks, that capture is a direct removal for them. They own and control the equipment.
Okay, that's clear. So what's an indirect emission?
An indirect GHG emission is an emission that occurs as a consequence of the organization's activities, but it happens at sources that are not owned or controlled by that organization.
The classic example is electricity, isn't it?
That's the perfect example. Your company uses electricity in its office building. That electricity use is part of your operations. But the emissions created when that electricity was generated happened at a power plant, likely owned by a separate utility company.
So the emission isn't physically happening at my site, but my demand caused it.
Exactly. Your electricity consumption is the activity, but the emission source, the power plant, is outside your direct control. Other examples include emissions from business travel, airline emissions, emissions from transporting your products in trucks owned by another company, or emissions embedded in the raw materials you purchase.
This distinction seems really crucial for getting a full picture.
It's fundamental for accurate accounting and responsibility. If organizations only reported their direct emissions, we'd miss vast swaths of climate impact related to energy use, supply chains, and product life cycles. The direct-indirect framework, often further broken down into Scope 1, 2, and 3 emissions in corporate reporting, tries to capture that full footprint.
Okay, one last piece of the technical language, factors and coefficients. These sound like the tools for the actual calculations.
They're the conversion keys used in the inventory map. The GHG emission factor is a coefficient that relates your activity data to the resulting emission.
Activity data
Like the amount of fuel burned, liters of gasoline, tons of coal, the amount of electricity consumed, kilowatt hours, the amount of product manufactured, etc. The emission factor tells you how much GHG, usually in kg or tons of CO2e, is emitted per unit of that activity.
So X amount of coal burned times the emission factor for coal equals Y amount of CO2e released.
Precisely. And similarly, there's a GHG removal factor. This is the equivalent coefficient that relates activity data for a sink, like the area of forest planted, or the volume of CO2 successfully captured and stored with the amount of GHG removed from the atmosphere.
So these factors are essential for turning real-world activities into standardized GHG numbers.
Absolutely. They're the bridge between the complex science of warming potentials and the practical task of counting emissions and removals based on measurable activities. All these definitions, monitoring, source sink reservoir, direct, indirect, emission factors, they form the complex but necessary language needed to manage GHGs globally.
Yeah.
And all this detailed science, all this careful inventory language, it ultimately has to inform the response, the political response, the policy response.
Because as the source material really stresses, climate change isn't a problem one country can solve alone, is it?
Not even close. It's the ultimate global commons problem. My emissions affect your climate, your emissions affect mine. Regardless of borders, it requires a massive amount of international cooperation, which is, frankly, incredibly difficult to achieve.
But attempts have been made. The sources point specifically to the Kyoto Protocol as a major early effort.
Yes, Kyoto was landmark. Negotiated in Kyoto, Japan back in 1997, actually, but the final details were hammered out and it was formally adopted later, signed by many countries, including in Bonn in 2001. Eventually, 186 countries became parties.
And what was its core goal? What did it require countries to do?
It was the first international agreement to set legally binding greenhouse gas emission reduction targets for industrialized countries.
Legally binding. That's important.
Very important. The requirement was that these participating industrialized countries had to reduce their collective emissions of 6 key greenhouse gases.
Which ones?
Yeah.
The main ones we've discussed.
Yes. CO2, methane, CH4, nitrous oxide, N2O, and those 3 major families of F gases, HFCs, PFCs, and the superpotent sulfur hexafluoride, SF6.
And they had to reduce anthropogenic emissions, right? The human-caused ones.
Correct. The focus was explicitly on emissions resulting from human activities, not natural cycles.
And what was the specific target? How much reduction?
The overall target was quite specific. Collectively, these countries had to reduce their emissions by at least 5% below their 1990 levels.
Below 1990 levels, so using 1990 as the historical baseline year.
Exactly. And this reduction had to be achieved during the first commitment period, which ran from 2008 to 2012.
So it set a concrete target, a baseline, and a time frame, a real benchmark.
It did. It signaled a global acknowledgement, at least among signatory nations, that emissions needed to not just stabilize, but actually start coming down from historical levels.
But achieving those cuts, even 5% must have been challenging. Did Kyoto offer any help or flexibility?
Yes, and this was quite innovative at the time. The architects of Kyoto realized that the costs of cutting emissions could vary wildly from country to country and sector to sector. So to make the targets more achievable and economically efficient, they introduced 3 market-based flexibility mechanisms.
Market mechanisms, how did those work?
The first one was emissions trading, which most people now know as cap and trade. Basically, countries had emission allowances, or caps. If a country reduced its emissions below its cap, it could sell its surplus allowance to another country that was finding it harder or more expensive to meet its own target.
So it created a market, a financial incentive to cut emissions more cheaply.
Precisely. Money flows to where the reductions are cheapest to make. The second mechanism was joint implementation, or JI.
Joint implementation, what was that?
JI allowed an industrialized country, one with a Kyoto target, to invest in an emission reduction project in another industrialized country, also with a target, and earn emission reduction units, or ERUs, for doing so.
So country A pays for an upgrade in country B and gets credit towards its own target.
Essentially, yes. It encourages investment in cleaner technology across borders between developed nations. Both countries could benefit.
Okay, and the third mechanism?
The third was perhaps the most significant in terms of global reach. The Clean Development Mechanism, or CDM.
Clean Development Mechanism. Sounds positive.
The idea was positive. The CDM allowed an industrialized country with a target to invest in an emission reduction or emission avoidance project in a developing country, which typically did not have a binding target under Kyoto.
Ah, so investing in the developing world.
Yes. The industrialized country would get certified emission reduction credits, CERs, which they could use towards meeting their own Kyoto target. The aim was twofold: help industrialized countries meet their targets more cost-effectively, as reduction costs were often lower in developing nations, and simultaneously promote sustainable development and technology transfer to the developing world.
So these three mechanisms, emissions trading, JI, CDM, they were built into Kyoto to make the overall goal more flexible and potentially cheaper to achieve.
Exactly. They recognized that a purely domestic command and control approach might be inefficient. These mechanisms were designed to harness market forces and international cooperation to find the lowest cost ways to reduce emissions globally, regardless of where those reductions physically occurred.
So to actually meet these targets, whether domestically or through these mechanisms, countries and the companies within them need concrete strategies. What kind of mitigation actions do our sources suggest?
They list several key approaches, and we can actually connect these directly back to the inventory language we discussed earlier.
Okay, how so?
Well, for instance, planting trees and forests is listed as a key strategy. In our inventory terms, this directly increases a GHG sink and helps build or restore a GHG reservoir, the forest biomass in soil.
Right. Reforestation, avoiding deforestation, critical sink activities. What else?
Other big ones are moving to renewable energy sources like solar and wind, encouraging green industry and transportation like electric vehicles or more efficient manufacturing, and recycling our wastes.
And those actions primarily reduce.
They primarily reduce the GHG sources. They cut down on the direct emissions from burning fossil fuels for power and transport, and also the indirect emissions associated with energy consumption and the life cycle of products.
The sources also mention creating parks for endangered animals. Is that directly related to GHGs?
It's more broadly related to ecological health. While protecting biodiversity hotspots might have some co-benefits for carbon storage if it involves preserving forests or wetlands, it's listed more as a general environmental solution alongside the specific GHG mitigation strategies.
Got it. And there was a point about influencing companies.
Yes, a crucial one: persuading enterprises to stop polluting. This often involves a mix of regulation, economic incentives, like carbon pricing, and also voluntary industry initiatives, sometimes called responsible care activities, where companies commit to better environmental performance and transparency.
Because ultimately, corporate operations are where most emissions originate, directly or indirectly.
Exactly. Their buy-in and action are absolutely essential. This ties everything together, highlighting the importance of GHG mitigation through effective energy management and cleaner industrial processes within businesses. They need to use the inventory tools and respond to the policy signals set by agreements like Kyoto and its successors. #tagoutro. So, looking back, we've covered a huge amount of ground today, haven't we? We went all the way from the frankly, amazing foresight of Svante Arrhenius back in 1896.
Yeah, that 1896 prediction, realizing the potential link between fossil fuels and warming, that's still mind-blowing.
And the fact it took nearly a century to fully verify his calculations just shows the sheer complexity and patience involved in climate science.
Then we quantified the problem. We looked at how different gases have vastly different warming impacts using the Global Warming Potential Index.
Right, grappling with those numbers. CO2 is 1, methane maybe 21 or higher, N2O at 310.
And then the industrial gases, culminating in sulfur hexafluoride SF6 at nearly 24,000 times the warming potential of CO2 per kilogram. Just staggering potency.
And we saw the scale 50 billion tons of CO2 equivalent globally per year. Tracking that requires this really specific, structured language.
The language of inventory. GHG sources adding to the atmosphere, GHG sinks removing from it, and GHG reservoirs storing it.
And crucially, distinguishing between the direct emissions an organization controls and the indirect emissions it causes through its value chain, like buying electricity.
That detailed accounting isn't just academic, is it? It's the essential foundation that allows global policy to even function.
Absolutely. It feeds into agreements like the Kyoto Protocol, which set those first binding targets and introduced those flexible market mechanisms, emissions trading, JI, CDM, trying to make reductions happen efficiently across borders.
So the science is clear. The problem is quantified. The technical tools for tracking are there, and policy frameworks exist, even if they're constantly evolving. We know the physical impacts are happening. That Arctic ice shrinking by 13.4% per decade is a stark reminder.
And we know where the bulk of the problem originates geographically, those top 10 countries responsible for up to 70% of emissions.
So here's the final thought, the question maybe to leave you, our listener, mulling over. We know the climate models are constantly being updated, the science refined. We have these established policy tools like market mechanisms and these detailed inventory systems that track direct and indirect footprints.
Given all that, what immediate leverage point do you think holds the most promise right now for driving the rapid change this data clearly demands? Is it tightening those international policies? Is it better use of market mechanisms like the CDM to drive investment where it's needed most? Or is it maybe focusing intensely on that corporate accountability, using the inventory data to really pressure companies on their full scope 1, 2, and 3, their direct and indirect emissions?
Where's the point of maximum impact right now?
That's the multi-trillion-dollar question, isn't it? Where does our effort yield the fastest, biggest return?
A challenging thought indeed. Thank you so much for joining us for this deep dive today. We hope exploring this intricate web of history, science, potency, and policy around greenhouse gases has been valuable.
Keep digging into the sources, keep asking questions.
And we'll catch you next time on The Deep Dive.